Suppose x and y are two jointly distributed random variables. We have combined x and y using some known function h to construct a new random variable z. And we are interested in expected value of z. Now, one technique to find this could be to use the definition directly. Just work out the distribution of z, and z being a univariate random variable, a single random variable, you can apply the general definition to find out expected value of z. But a simpler alternative exists. If z is always non-negative, then expected value of z may be obtained using this formula, where this f is joint density of xy. So this formula is for the case where you have a joint density. Now, since the integrand is non-negative, this is non-negative because of this, and density is always non-negative. So this integral is always bound to exist, though it may be infinite. And in general, that is, if this non-negativity condition is not present, then we can proceed in the usual way. We define z plus and z minus. This takes care of the positive part of z and this takes care of the negative part of z, but both these random variables are actually non-negative. And then we define expected value of z as expected value of z plus minus expected value of z minus, which is the general prescription, and it's natural because we have z equal to z plus minus z minus. This definition is actually a consequence of the general definition of expectation in terms of supremum, etc. that we touched upon in the last semester. I do not expect you to remember all those things right now, but I will just remind you that this is a consequence of that. How this definition comes from that definition will be clear once we learn about Lebesgue integrals near the end of this semester. And incidentally, if this is infinite and that is also infinite, then we say that this is undefined. Now this format, this particular formula is very much similar to the univariate case. Unfortunately, this does not always hold. Even in the univariate case, it does not always hold. One condition when it holds is if it is always non-negative. If it is not non-negative, we have to go into all the hassle of z plus and z minus. But this theorem is going to give you another condition under which also you can use this. And that condition is if absolute value of z has finite expectation, absolute value of z is non-negative, so its expectation must always exist. It could be finite or it could be infinite. Now, if it is finite, then expectation z is also finite. It could be negative, but it is finite, and we have this thing. Now, this is what we have most of the time. So usually this condition will be satisfied, and so we can find out expectation by just multiplying it with the density and taking integral over the entire space. The proof of this theorem is pretty straightforward. Once you notice that absolute value of z is actually z plus plus z minus. So if this has a finite expectation, each of them must have finite expectation, and then by doing a little jugglery, you can arrive at this. We shall not pursue the proof here. You can try your hand at it yourself. In this problem, you are given xy that has uniform distribution over this set S, which is a subset of R2. Your final aim is to be able to find expected value of x times y and these two are steps leading to it. The first step is to sketch S, that is sketch it as a shaded subset of R2, and in part 2 you have to find the joint density of XY. Remember, I have said it has got uniform distribution over S, which means that the joint density will be a flat surface, flat horizontal over S, and you have to find the height of that flat surface. That's a constant, and it should be 0 outside S. Once you have done that, you have to find the expected value of XY. Since they are all non-negative, so you can use the expectation formula using integration.